Okay, hello everyone, and welcome to this presentation, which will be about automated security response through online learning with adaptive conjectures. My name is Kim, and this is joint work together with Tao, Rolf, and Quan Yan. So a challenge that we face in analytical modeling is that whatever model that we decide to use, it will never be a perfect fit of reality. We cannot hope even to capture all the details of a real system in the model. And this means that whatever model that we decide to use, it will always have some degree of what we call model misspecification. And this paper is about how we can manage and how we can quantify this misspecification. In particular, our main contribution is an online method for learning security strategies where the operator of the system does not need to have a perfect model. Rather, it only needs to have some conjecture about the model, and that conjecture may even be misspecified. Now, to present this method, I will focus on a security response use case that involves an IT infrastructure that you see here to the right, which consists of a set of connected components that jointly provide services to a client population. And this infrastructure is operated by an organization that I refer to as the defender, which monitors the network and may take response actions. In addition, there is an attacker that seeks to intrude on the infrastructure and wants to compromise components. And our goal here is to find automated strategies for responding to the attacker in real time. And the traditional approach to solve this problem, and you'll find many examples in the literature, is that you start out by creating a model of the infrastructure, which typically is going to be a game between the attacker and the defender. And then you make the assumption that this model is correct. So this is the ground truth of reality. And given that assumption, the common solution approach is that you compute optimal strategies or equilibria offline. By contrast, in this work, we do not make that assumption, and we instead focus on online learning of security strategies, where the players of the game may have misspecified models of the system. Specifically, we consider the following problem. So we have a partially observed stochastic game gamma, which is parameterized by some parameter vector theta that represents the dynamics of the underlying system. And this parameter vector is hidden from the players, but each player may have a conjecture about the parameters. And furthermore, as the game is being played, these parameters may be updated. They may change. It's a non-stationary game. And that means that the players may also need to update their conjectures and adapt their strategies. And our main question that we want to answer is, what is an effective method for doing this kind of learning online? And our solution to this problem is what we call conjectural online learning, which is a method that consists of two main components. First, we use Bayesian learning to adapt the conjecture about the model of the system. And second, we use rollout, i.e. look-ahead optimization, to update the strategies of the players. Specifically, when the player picks an action based on its strategy, so in the defender's case, this could be a response action like updating the firewall or access control or rebooting a machine, for example. Then the player will then receive some information feedback. And this could be any feedback that you can measure from the system. So it could be, for example, IDS alerts, login attempts, performance indicators, alerts, etc. And the player will then use that feedback to update its conjecture about the model of the system using Bayesian learning. And that then results in a posterior distribution over different models, which the player then uses to sample a particular conjectured model. And then it uses that conjecture to compute a new strategy using rollout. So this rollout procedure works as follows, where we take the conjectured model and then we simply roll that forward in time, a few time steps, to predict the outcomes of different actions. And in particular, we predict them in terms of the cost and in terms of the next state, or belief state in this case. And then we simply pick the action that minimizes the expected cost based on these predictions and based on this look-ahead tree. And here's exactly what I just said, but in terms of an equation. So the player has a strategy and a current belief state, and then we have this operator here, which we call R, the rollout operator. And that simply says that the player should update its strategy to pick an action that minimizes the expected cost under the conjectured model for L time steps into the future, where L is the look-ahead horizon. And by doing that, we are guaranteed that the updated strategy will always improve the previous strategy with respect to the conjectured model. And that is expressed by this inequality that you see here, where J is the conjectured cost to go function. Now, this, however, does not tell us anything about the performance of the rollout strategy with respect to the actual model, only with respect to the conjecture. However, unfortunately, it's very hard to say anything about the true model since we don't even know what it is and we make no assumptions about the true model. But what we can say at least is that if our conjectured model can predict the game at least one time step into the future, then we can bound the performance of the rollout strategy using the following inequality, where on the left-hand side, you have the suboptimality gap of the rollout strategy, and on the right-hand side, you have the suboptimality gap of your previous strategy. And then you have this term here in front of the norm on the right-hand side, where gamma is a discount factor, which is strictly positive and strictly less than 1. So this means that as you increase the look-ahead horizon L, this term will go to 0 at an exponential rate. So in other words, as we increase the look-ahead horizon, we shrink the suboptimality gap of the rollout strategy. However, there is, of course, or unfortunately, a trade-off here, because as we increase the look-ahead horizon, we also increase the computational costs exponentially. And that is shown in this figure that you see here. So this means that in practice, you can typically only do a couple of time steps of look ahead, but this really depends on your scenario and also depends on your computational capacity. So that's the first step of the method, where we have seen now that given a conjectured model, how we can update our strategy in a way that we obtain pretty good performance guarantees. In the second part, we will look at how we adapt the conjectures and obtain the conjectures in the first place, actually, using Bayesian learning. So the way it works is that whenever the player receives any feedback from the system, it uses that feedback to update its conjecture using Bayes' rule, as you see here. And the main question that we want to answer is, what happens when you do this learning for a long period of time? Will you converge? And if you converge, then what model will you converge to? Now, you may expect that we should converge to the true model, but that is not necessarily the case, because as I mentioned earlier, it's very, very likely that the players will have misspecified priors, meaning that they may assign 0 probability to the actual model, the true model. And then the question is, if we have that type of misspecification, then what will we converge to? And it turns out, as I will show, that we converge to a set of conjectures that are consistent in the following sense. So let me first define nu to be an occupancy measure over the belief space. And you can think about the belief space more or less as a state space. But since we have a partially observed environment, it's going to be a belief rather than an actual state. So the occupancy measure essentially tells you how frequently you visit different parts of that space. And this means that if you have an occupancy measure at time t, that basically summarizes how we have played the game up until time t. And given that measure, we then say that a conjecture at time t is consistent if the feedback distribution induced by the conjecture, so this distribution here, if that distribution minimizes the KL divergence to the feedback distribution of the actual model. So remember that we're doing Bayesian learning based on the feedback. And that means that the best thing that we can do as a learner is to focus on conjectures, focus on models that are the most consistent with whatever feedback that we obtained. So you want to focus on models that are likely, have a high probability of generating the feedback that we observed. And here's an example to make this a little bit more clear. So here in the dotted red line, that indicates the actual model, which in this case is just a scalar, which is equal to 1. And the black curve shows the conjecture distribution of the defender in this case. So if you start looking at time equals 1 here, then we can see that the defender has a uniform prior between 0 and roughly 0.8. And this means, of course, that the defender is misspecified because it assigns 0 probability measure to the actual model, which is over here at 1. And then you can see, as we are doing Bayesian learning, the conjecture of the defender is moving closer and closer to this dashed line that you see here, which is the set of consistent conjectures. Now it turns out that in this particular example, the set of consistent conjectures are also closest to the true model in the Euclidean sense, but that does not have to be the case in general. And furthermore, this convergence that we observe here is not a coincidence, it's actually a property of our method. So as you run our method long enough, then in the limit, the conjectures of every player in the game will concentrate completely on the set of consistent conjectures, as expressed by this theorem here. So in other words, the conjecture distribution of each player will assign 0 probability measure to any conjectured model that is not consistent with the feedback that has been observed. Okay, so that concludes my formal description of our method, and you can find more details if you're interested in the paper, but just to summarize, it consists of 2 main steps. We use rollout and a conjectured model to compute the new strategies, and we use Bayesian learning to update the conjectured models over time. And now I will go into some experimental results of using this method. So the scenario for the evaluation is shown here. We have a target infrastructure that you see to the right that consists of 64 different servers, which we run on our testbed. And these servers provide services that are consumed by the clients. And the feedback for the defender in this particular example are IDS alerts, which are generated here, 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 and here. So we have 4 different IDS in the system. And the response action for the defender in this case is that it can recover certain servers at a given cost. But the challenge, of course, for the defender is that it doesn't know which servers are compromised. And for the evaluation, I define the hidden parameter to be the number of clients. And I emulate arrivals of clients using this rate function here, which is a combination of a periodic term and a polynomial term that represents the trend of the arrivals, which is slightly increasing in this case, as you can see here. And I think that this parameter, the number of clients, is quite interesting because it's strongly correlated with the feedback that the defender will observe. So here are some measurements from our testbed, where you can see that the more clients there are, the more IDS alerts there will be in general. So essentially, more clients means more noise, more traffic on the network, and that in turn leads to additional false alarms. So as a consequence, if the defender knows exactly how many clients there are currently, then it can more accurately detect the attacker. And here are some experimental results of running our online method on this particular scenario. So the first scenario that I want to emphasize here is that when the hidden parameter theta keeps changing, as you see here, then clearly the conjecture that you see in blue will not converge. So it will try to track the changing parameter as good as it can, but since it is tracking a moving target, it obviously will not converge. So I just wanted to emphasize that. So the theorem that we saw earlier, it only applies when the parameter has stabilized or become stationary. And here's an example of such a case where I fix the parameter, the hidden parameter is fixed to be 12, the number of clients. And as soon as it becomes fixed, you can see that the conjecture of the defender converges very quickly and concentrates on the set of consistent conjectures as predicted by the theorem. And the corresponding convergence of the KL divergence can be seen in the bottom here. And when we look at the convergence rate, we can see that this depends on the prior of the defender. So let's assume now for the example that the defender has a uniform prior over some set capital theta. Then, as we can see in the plot, as we increase the size of this set, as basically makes the defender more uncertain about the hidden parameter, then it takes longer to converge to the consistent conjecture. However, we also notice something interesting, and that is that when you have the size of sufficient size and you make it even larger, it doesn't really affect the convergence rate that much. So this increase in the convergence time stagnates after a while, as you can see. Now, if you're interested in many more experimental results and much more details about these experiments, it's available in the reference that I provided at the bottom of the screen. And you're very welcome to check that out and reach out if you have further questions. But for this presentation, I will conclude by summarizing and saying that in this work, we present a novel game theoretic formulation of security response, where each player has a conjecture about the model. And based on that formulation, we have presented an online method for learning security strategies, and we have proven that this method has certain performance and convergence guarantees. Thank you very much for your attention.